The ultimate ambition of data-driven physical emulation is to bypass expensive numerical solvers. Instead of calculating partial differential equations step by step, we want a model that can forecast continuum dynamics directly from historical states. But when we try to apply the foundation models that revolutionized natural language and computer vision to this problem, they fail. Those architectures are built to consume highly homogeneous, uniform data inputs. Text tokens and standardized image patches are predictable. Physical data is extreme in its heterogeneity. A single scientific dataset might span wildly different temporal scales, fluctuating spatial resolutions, and completely disparate physical fields. Then there is the dimensionality problem. Physical data exists in fundamentally incompatible shapes. You cannot natively feed a mix of two-dimensional planar slices and three-dimensional volumetric data into standard training pipelines without stripping away critical geometry. When standard vision transformers attempt to process this data for long-horizon autoregressive prediction, the outputs rapidly degrade. This degradation manifests as a physical collapse. Compounding, grid-like artifacts accumulate over time and completely destroy the coherence of the simulation. Treating continuous physical dynamics like scanned images or text inevitably leads to network collapse. Solving this requires a complete architectural rethink. This is Walrus, a 1.3 billion parameter transformer designed specifically for fluid-like continuum dynamics. Its pre-training data spans 19 highly diverse scenarios. The model ingests everything from astrophysics and plasma physics to rheology and classical fluids. By integrating both two-dimensional and three-dimensional data, it achieves state-of-the-art short- and long-term prediction across these distinct scientific domains. To achieve this downstream performance, the researchers utilized a training methodology that intentionally degraded their own standard pre-training efficiency. Rather than homogenizing data to make it easy to digest, researchers forced the model to ingest data in its native, chaotic state. To understand why worse pre-training metrics lead to better physics emulation, we have to deconstruct the three architectural interventions Walrus uses to process reality. The first structural barrier is standardizing two-dimensional and three-dimensional data so it can pass through a shared encoder-decoder without stripping its physical properties. Walrus begins by treating all 2D data as a thin plane within a larger 3D space. It does this by appending a singleton dimension and zero-padding the tensor-valued fields. Next, it applies tensor law-aware augmentations, specifically the full octahedral group of 90-degree rotations and reflections. This locks the previously flat two-dimensional plane into a random, arbitrary orientation within the three-dimensional volume. This operation forces the network to learn generalized, dimension-agnostic spatial representations, preventing it from overfitting to axis-aligned 2D grids. But this creates a compute bottleneck. When you have mixed resolutions, standard distributed training suffers severe load imbalances because patch-based tokenization ties computational cost directly to spatial resolution. The solution to this load imbalance is a mechanism called convolutional stride modulation. Convolutional stride modulation dynamically alters the downsampling stride during pre-training. It enforces a fixed number of tokens per axis, 32 per dimension for 2D data and 16 per dimension for 3D data. Combining the 3D projection with this stride modulation standardizes the computational load across the cluster without homogenizing the underlying physical structures. The second major barrier is long-horizon rollout stability. Prior research often blamed simulation instability on complex nonlinear effects, but the Walrus team isolated the root cause to standard vision transformer petrification itself. Specifically, the problem lies in the resampling operations used to tokenize data, strided convolutions used for downsampling, and transposed convolutions used for reconstruction. This chart visualizes Lemma 3.1. Even in a perfectly idealized, linear setting, these resampling operations inherently create spectral artifacts.
Looking at the frequency response, the summation terms represent aliased frequencies. These are high-frequency errors injected directly into the signal simply by the act of applying a stride. Because the model is autoregressive, it feeds these high-frequency artifacts back into itself at every single time step. These linear resampling operations mathematically guarantee that high-frequency noise will compound. They grow into rigid, grid-like imprints that destroy the emulation. To solve this, the researchers introduced Proposition 3.1, a technique called patch jittering. During each autoregressive step, the model applies a random phase shift, a translation, to the input data right before tokenization. After the model reconstructs the output via transposed convolution, this exact translation is mathematically inverted. By exploiting the Fourier shift property, the aliased high-frequency terms cancel out in expectation. Because this acts as a Monte Carlo averaging procedure, the error converges to zero as the rollout continues. Empirically, this simple stochastic shift reduces long-horizon error in 84% of all pre-training scenarios. Patch jittering solves the structural stability problem with effectively zero computational overhead, allowing the architecture to maintain coherence indefinitely. The combination of convolutional stride modulation, dimensional embedding, and patch jittering enables Walrus to process highly heterogeneous data without collapsing. We can see the results in this two-dimensional slice of a fluid simulation. The model successfully tracks fine heat variance and intricate turbulence patterns over long temporal horizons with no visible grid artifacts, and this stability scales perfectly into 3 dimensions. Complex 3D structures, like these translucent fluid wisps, maintain their physical boundaries and density gradients without succumbing to aliasing noise. But while this architecture is highly stable, achieving it required forcing the model through an incredibly aggressive, diversity-first training environment. The aggressive augmentations, mixed dimensions, variable time strides, and random rotations make the pre-training task significantly harder for the network. This chart displays the results of an ablation study comparing a fully augmented half-walrus model against a naive 2D-only baseline. On the left, the fully augmented model suffers from higher loss during pre-training, but on the right, that same augmented model drastically outperforms the naive baseline on downstream transfer tasks. According to standard machine learning heuristics, the model with higher pre-training loss should be inferior. But in scientific machine learning, this harder pre-training environment yields vastly superior low-shot transfer performance. The most extreme proof point of this study involves a Walrus variant pre-trained exclusively on two-dimensional data, utilizing the full suite of 3D projection augmentations. When tested, it successfully generalized to out-of-distribution 3D astrophysics datasets. This 2D trained model had never seen a 3D dataset in its life, yet it outperformed models trained from scratch on that exact 3D data. Standard machine learning pre-training loss is a misleading metric for physical emulation. Forcing the network to struggle through heterogeneous augmentations ensures it learns invariant physical laws, rather than just memorizing a unified dataset. Applying standard heuristics from natural language processing and computer vision directly to continuum dynamics simply does not work. Scaling up parameter counts and data volume is insufficient if the underlying architecture mathematically introduces aliasing through its linear operations. Models like Walrus succeed precisely because they integrate specific mathematical interventions like patch jittering and stride modulation, designed explicitly for continuous fields. The critical lesson for the scientific machine learning community is that chasing artificially low pre-training loss by homogenizing datasets is a trap that limits generalization. True generalized physical emulation requires abandoning homogeneous pipelines and building architectures capable of ingesting reality in its native chaotic state.